Our next topic is covered by chapters 12 and 13. We're going to start with chapter 12, which is on waves and vibration. The first thing we're going to look at is simple harmonic motion. Simple harmonic motion is vibration about an equilibrium point. And this is where a restoring force, restoring the object to its equilibrium position, is proportional to the object's displacement from equilibrium. A couple of examples of harmonic motion would be an object bouncing on a spring, a pendulum swinging back and forth. Waves and oscillations have some similar properties. Those are amplitude, period, and frequency, and we'll take a look at how those are defined with these first. The amplitude is the maximum displacement of the oscillations from equilibrium. Amplitude is a measure of how much energy the oscillation is transmitting. The period of the oscillation is the amount of time it takes for the cycle to go through once, whether it's an oscillation back and forth or a wave traveling. Usually period is measured in seconds. Frequency is the number of cycles in a particular unit of time. Cycles per second, oscillations per second, or waves per second. It turns out that frequency and period are inverses of each other. So 1 over the frequency equals the period, 1 over the period equals the frequency. One of the things we'll take a look at in class is a pendulum, and we'll look to see what variables might affect the period of the pendulum. What ultimately we should find is when we're looking at a pendulum, the period of the pendulum depends really only on the length of the string. And the equation for that looks like this. So the period, or the time for the pendulum to swing back and forth, is equal to 2 pi times the length of the pendulum over g, square root of that value. Well, is the string length, or the rope or the cord, or whatever the pendulum uses to suspend the pendulum bob. G is gravitational field strength. In this case, restoring force is gravitational force, because when the pendulum is at its full extension, gravitational force is what restores it back to equilibrium. So equilibrium would be right there. As the bob mass gets heavier, the heavier bob mass provides a larger restoring force because Fg is going to be bigger, but it also requires a larger force to create the acceleration it experiences. The larger amplitude also creates a larger restoring force. So if we bring it up higher, it's going to have a larger amplitude. It has a larger acceleration, but it also has to cover a larger distance, so the period is the same. Let's take a look at an example of this. We have a pendulum suspended from a ceiling. It almost touches the floor at its equilibrium position, so when it's hanging straight down perfectly vertically. If it has a period of 12 seconds, how high is the ceiling? Well, let's see if we can figure that out. So our equation is period equals 2 pi times L over G. So we are looking for L, the height of the ceiling. So we can reorganize this. So the period over 2 pi, and that quantity getting squared, times G gives us the length. So our period is 12 seconds over 2 pi. We'll square that. G is 9.81, and that equals the length of our pendulum string. And what we find is we get a length of 35.8 meters. If we take a look at a mass spring system where we have a mass oscillating on a spring, either hanging from a spring and bouncing or being pushed up by a spring, what we find is that the period of this system depends both on the mass of the spring, because that is the restoring force, and the spring constant. Turns out a heavier mass takes more time per cycle because it has a smaller acceleration. So if we increase the mass, we increase the period. If we have larger spring constants, they require more force to stretch or to compress the spring, and a larger force creates a larger acceleration. So for a spring, the formula is going to look a little bit different compared to a pendulum. So we have the period in this case is 2 pi times the mass on the spring divided by the spring constant, and this now is square rooted. So if we take a look at an example of a problem like this, we have a car frame supported by 4 springs. and each spring has the same spring constant. We have two people in the car with a combined mass, and we want to find out the period of vibration of the car as it's bouncing over potholes. So we're looking for period. So we'll use our spring equation. All right, the mass is going to be the mass of the car plus the people in the car. So a total mass is 1428 kilograms. But because we have 4 springs, each spring roughly supports 1/4 of that. So each spring supports 357 kilograms. And each spring has the same spring constant, that's K, and that's 2 times 10 to the 4th. And so now we have the numbers, we can just put it into our equation and find out what the period is. So our period is 2 pi times the square root of 357 divided by 20,000. So we end up with a fairly small period of 0.839 seconds.